Hello, everyone. Thank you very much. My name is Shadi Momtahen, and I am a PhD candidate in the School of Mechatronic System Engineering in Simon Fraser University, at Simon Fraser University in Canada. And my co-authors are Dr. Shukufi, Dr. Ramani, and Dr. Golnaraghi. And this work is collaborated with BC Cancer in Abbotsford. Just let me start with presentation outline. In this talk, I'm going to introduce to you our work in breast cancer with our device, the diffuse optical breast scanning or the Obscan Pro. In the first part, I will talk about its background, the theory and instrument design. And then I just briefly talk about our recent work in diffusion equation modification, MDE model, that we have just modified the existing theory, diffusion equation. Okay, just let's start with breast imaging modalities. There exist different methods and modalities for breast imaging, such as mammography, ultrasound, PET scan, and other devices. But all of these devices have some limitations. For example, mammography has been the gold standard, but it has some problems. It is not recommended for women under age 50. It is difficult to detect breast cancer for women with dense breasts. And also, it is a painful procedure. Squeezing two breasts inside two places is painful. The other problem that for mammography is that it has a potential health risk due to using, X-ray or ionizing radiation. The other device is ultrasound. Ultrasound can detect breast images which are dense, better than mammography. It has higher sensitivity, but it can tell something is here. It cannot tell whether this is cancer or it's not cancer. It has low specificity. The other device is MRI. If we use functional imaging, MRI is a very good device. It can be very accurate, but it has some problems. It is very expensive, 10 times more expensive than mammography. It is not portable, it is not accessible. Also, functional imaging is not suitable for different types of cancer. PET scan, unlike X-ray and mammography, can detect cancer in its early stage, but it has some problems, such as it has low resolution. As you can see, all of the dimension devices have some disadvantages. And so we have developed a device. This is our device. It works, it is based on near infrared diffuse optical tomography or TOT. That this is safe, it is painless, it is not very expensive, and it does not use radiation, X-ray radiation, and it can detect cancer in its early stage. Okay, just as I told, we use near infrared. Just let me describe about near infrared region. This is near infrared window. As you can see, it uses from 650 to 1000 nanometer wavelengths. And the reason behind using near infrared is that the main constituents in breast tissues are oxyhemoglobin or oxygenated blood, deoxyhemoglobin or deoxygenated blood, water and fat, as you can see here. These main constituents have different characteristics, unique characteristics, dependent on the wavelengths. So we can use 4 wavelengths to identify these main constituents in breast tissue. Okay. This is our device, the Obscan Pro. As you can see here, it has 2 ELEDs. And this is the device. And each ELED has four light source. One at 690 nanometer wavelength, 750, 800, and 850 nanometer wavelength. And also it has a detector. You can see this is CCD array, or here, this is CCD array. It has 128 pixels or sensors on it that can just detect and just after detecting by using this sensor, it can combine the result and just send one signal, transfer one signal from this probe to this computer. I will talk about the travel procedure just from light source. Light enters through the tissue and just comes back. The intensity of the tissue comes back through the device and comes back to the computer, and some analysis will be conducted in the computer. Just let me describe this procedure. I mean, light transport inside breast tissue. Suppose these black areas here, these black arrows here are light, which is entering the tissue. We have a source here, light source, I mean. Light entering the tissue, some of the light is absorbed, light is entering, some of the light is scattered, some of the light is back scattered, and detector is here. And the detectors just can collect the intensity of this back scattered light and just use it and just transfer it to the computer. As I mentioned, diffusion equation is the theory behind this procedure. It tells how much the light is absorbed, how much the light is scattered, or it talks about the optical property of the tissue. It just measures it and just calculate the intensity. And after that, doing some algorithm using some algorithms on the computer system, we can reconstruct the images. As you can see here, we have these images from our clinical study in 2016 and 2017. We just used the data from 20 patients. We tested our probe on this on the cancer breast, and also we used normal breast. We use normal breast as our reference. These patients were at Jim Pattison Outpatient Care and Surgery Center, and Dr. Rhonda Jansen was supervising this procedure. She is a surgical oncologist, and doctors told us for this case, it is an example of one of our patients' result. They told us left breast is cancerous. As you can see, the probe could successfully identify the tumor here. This dark region shows the tumor inside this red region. The red region shows higher concentration of hemoglobin because it is at 690 nanometer, which is associated to hemoglobin. And you can see for left breast, all of the wavelengths, all of different four wavelengths can successfully identify the tumor. And this is for right breast. There is nothing here. It does not show anything. This small light here is some noise. We can ignore it. And just before doing such experiments and just just generating such images, we conducted some studies with our phantoms. Phantoms are a scattering medium that has some optical properties to breast tissue. We just have three kinds of phantoms. For example, we have Derlin solid phantom. You can see here it is Derlin solid phantom. It has a cylindrical shape, and this Derlin phantom just has the optical property similar to breast fat. It can mimic breast tissue. It usually has a hole, as you can see here. We can insert an Allen key here that mimics a tumor inside this phantom. We usually use absorbers such as key, ink, or dye that just mimic tumor inside our phantoms. And if we add absorbers, more absorbers, we can just get data that is more similar to patients' data. Also, we have two different kind of liquid phantoms. One of them is intralipid liquid phantom. Intralipid solution is a soy-based liquid phantom, and liquid solution, it is just diluted with pure or distilled water, and just we generated and prepared different varying concentration of liquid phantom with intralipid. Then we added Indian, black Indian ink to it, and just we prepared 36 different liquid phantom solutions with different ratio of ink concentrations. Okay, just in this slide, I'm just going to talk about the modified diffusion equation, our working the theory, the improving the theory. I just talk about the probe data collection here, and just I'm going to describe this equation. This is our theoretical theoretical equation that we suggested, and the modified equation, and these figures and error analysis. Before that, just let me talk. I told you there is a breast tissue, and just probe is here to collect the intensity of this breast tissue. And this intensity, this measured intensity, is a function of the distance between source and detector, and the light intensity, I mean the source light intensity, and integration time of the collector. I mean, integration time is the time that the probe is collecting light, and also the properties of the breast tissue. If we consider all of these factors, for one phantom, we can generate different sets of data. We don't want to have it. We want to have one data for one phantom. We want to adjust all of the data. Just we use our scaling model as just let me describe this figure. Uh, you can see by just changing light intensity from 192 to just increasing to 55. For one phantom, it is one of our designated phantom, is liquid phantom 171. And we have different sets of data. We don't want to have different sets of data. This curve just shows, represent measured intensity by the probe versus the distance or pixel numbers. You can see as the intensity decreases, the distance just increases. And we have used our scaling model. We have used several equations to just have one scale data, one experimental or actual data, one curve. This is the red curve here behind this the black dashed curve. And then we have the actual data here. And also this is the diffusion equation curve, the existing theory behind this procedure. And you can see the red dashed curve has some error. I mean, the actual data and the theoretical data, there is a discrepancy between these two data, because diffusion equation has some limitation due to some certain theoretical assumptions. It is idealized theoretically, but obviously it does not match to the experimental result. So we just modified diffusion equation. At first, we suggested a new equation. This curve is the result of this new equation. You can see this equation just can resemble diffusion equation. Both are exponential. And it can be diffusion equation. We just delete the b terms, and we just modified it. This equation gave us some idea, some hint how to modify it, and we modified it by adding some b terms to diffusion equation as just proposed. Modified diffusion equation, I mean, it's the black here superimpose the red line. You can see this is our new theoretical result, and it's perfectly matched the experimental curve, and we called it modified diffusion equation. We just did some error analysis and find out with minimum error that it can perfectly match the curve, and the error analysis shows 80% improvement for solid phantom if we use modified diffusion equation in compared to diffusion equation. Okay, let's talk briefly what I talked about in this presentation. I just talked about modified diffusion equation. It works with liquid phantom and solid phantom. And our next phase, our future work is improving our model by using artificial intelligence or neural network. And in the next phase, we are going to apply this method to our clinical study, as I showed you some images from our previous work. We are going to create some such images, but this is not subject of this work, it's our future work. Thank you very much. If you have any question, I am pleased to ask you.